Okay, now we're going to see mainly two theorems in this lecture, and these theorems are mainly deal with independent and identically distributed random variables. So these are these results are very useful in many areas of statistics, and so I thought that maybe I can, though the statistics is not part of this course, but this comes from the probability of or the normal distribution. So these results are quite helpful. So I thought that maybe I can introduce them here. Okay, so first result says that if x1, x2, xn are IID normal 0, 1 random variables, then the first theorem talks about what is the distribution of summation xi square. So if I have IID normal 0, 1 standard normal random variables, if I have IID standard normal random variables, the first theorem talks about what is the distribution of the summation of the square of the random variables. Okay, so the theorem says that this random variable summation xi square I equals to 1 to n has a gamma distribution with parameter n by 2 and half. Have a gamma distribution with parameter n by 2 and half. N is basically number of random variable present here. Note that two important thing. One is they has to be independent and identically distributed with standard normal random variable. So mean 0 and variance 1. Mean 0 and variance 1 is also important. So IID normal mean 0 variance 1, this is important for this result. So now how can I prove this one? That what is this thing? What is this thing? I am coming to this one, but first try to prove that that summation xi square follows gamma with parameter n by 2 and half. So how can I prove this one? I can prove this using moment generating function. So I can start with this one. First, suppose finally I need to find out what is the moment generating function of t, right? I need to find out what is the moment generating function of t. T is nothing but summation xi square. And when I try to find this one, I have to basically write that moment generating function of t as the product of moment generating function of xi at the point t. So I need to find out what is the moment generating function of xi at the point t. Sorry, it will be xi square. It will be xi square at the point t. So moment generating function of xi square at the point t. So the moment generating function of xi square at the point t by definition is this expectation, and then I know that xi has a standard normal distribution. So using the density function of the standard normal distribution, that can be written in this integration form. And now you can take x square equals to z, just make the transformation. You can transform it into a beta integral. Okay, first you need to understand that this is a even integral, so you can make it from minus 0 2 times 0 to infinity. Then you can convert into a gamma integral, or you can use the density function of normal distribution to do this integration. And once you do the integration, it turns out to be this one, and this integration only exists if t is less than half. This integration only converts if t is less than half. So that means the moment generating function of x1 square going to exist, or going to exist if t is less than half. And in this case, the moment generating function is given by 1 minus 2t whole to the power minus half. Okay, whole to the power minus half. So now the moment generating function of t, which is the product of the moment generating function of xi square, is nothing but 1 minus 2t whole to the power minus n by 2. And we know that this is the moment generating function of the gamma distribution with parameter n by 2 and half. So that's why basically summation xi square follow a gamma distribution with parameter n by 2 and half. Now, what is this part? This part basically, this distribution, that gamma distribution with parameter n by 2 and half, is given another name which is called the chi-square distribution. So it is called the chi-square distribution with parameter n, and in case of the chi-square distribution, the parameter is called degrees of freedom. Okay, so this distribution gamma n by 2 and half, this distribution is also known as the chi-square distribution with degrees of freedom n. Thus, this result shows that the sum of the square of n IID normal 0, 1 random variable has a chi-square distribution with degrees of freedom n. So, what is degrees of freedom? Just give a little bit intuitive idea of the degrees of freedom. Degrees of freedom basically mean that how many quantity you can choose freely. So, in this case, in the summation, in this summation term, I can choose each of the xi freely. That's why we call that the degrees of freedom is n. Okay, so that's why we call that degrees of freedom is n. In some example, in the next theorem, we are going to see that, well, I again will have a sum of some square quantity, but in that case, that all the quantities cannot be choose freely, and in that case, the degrees of freedom are going to reduce. Okay, fine. So degrees of freedom have some connection with our life also, like degrees of freedom is something that what level of freedom we are basically enjoying. Like when I was in hostel, I have lot of freedom that nobody sees me. I just spend my time, my life, what I want to do. This way, I mean, many of you also do this way also. But when now you are in home, so you have to obey some home rules. So your degree of freedom reduced. So in this way, okay. So the same kind of thing is true here, that in this case, in this sum, I can choose all the xi freely. So that's why basically degrees of freedom is n. In the next example, we'll see that we'll again have a summation of some square quantity, and in this case, the quantities cannot be all the quantities cannot be choose freely. So that's why the degrees of freedom is going to reduce. Okay. So let us see the next theorem. This is a quite interesting theorem. The proof is also very interesting from this theorem. This theorem tells that, well, if x1, x2, xn are IID, normal mu sigma square distribution. So I have mu, I have sigma square parameter, but they are still remain IID. Okay. In that case, the sample mean, which is x bar, and the sample variance, which is given by 1 s square, which is given by s square, which is 1 by n summation I equals to 1 to n xi minus x bar whole square. These two, x bar and s square, is given by these two expressions. So in this theorem, we are going to talk about the distribution of x bar and x square. So the interesting thing is that the x bar, which is basically average of all xi, going to follow again a normal distribution, but the parameter is going to change. The parameter, the first mu remains mu, but sigma square will be now sigma square by n. The variance will be sigma square by n. And then this s square, n minus 1 time s square by sigma square, that will going to follow a chi-square distribution with degrees of freedom n minus 1. So in this case, the degrees of freedom is not n, though I have a sum up to n. Okay, though I have a sum up to n, but in this case, the degree of freedom is not n, but it is n minus 1. And another important thing here is that these two random variables x bar and s square, these two random variables are independently distributed. Okay, so that this theorem basically says that if I have some normal random variables, IID normal mu sigma square random variables, if I see the sample mean, if I see the sample variance, they are independent. Sample mean and sample variance are independent random variables, and the distribution of the sample mean is normal with mean mu and variance sigma square by n, and the distribution of n minus 1 times sample variance divided by sigma square follows a chi-square n minus 1 degrees of freedom. Okay, let us give again the intuitive idea of the degrees of freedom for this s square first. So, what is s square? Note that s square is basically having something. I am having something like this: xi minus x bar whole square. Okay, I am having something like that. Obviously, I have some constant. The constant I am not bothering for this, finding out the degrees of freedom. That's why I am writing in this manner. So, suppose I call di is equals to xi minus x bar. How many di's are there? There are n di's. Okay. Now the question is that how many di's out of this n di's, how many di's I can choose free? Notice that what is the value of summation di I equals to 1 to n? That will be 0 because it is nothing but summation of xi minus n times x bar, which is basically nothing but this the first quantity is nothing but n times x bar. That's why this quantity is 0. So as the summation of all the di's is 0, that basically means that I cannot choose all the di's freely. I can only choose n minus 1 di freely, and the last di is automatically fixed. Okay, so that's why the degrees of freedom in this case is reduced by 1. Okay, clear? So let us now, that is obviously the intuition be behind the degrees of freedom. Let us now prove it using mathematical tools what we have already learned in this course till now. Okay, so how can I prove this one? The proof is little bit different. See, the direct transformation will not work here because I have n random variable here, but I need to find out the distribution of x bar and s square. So two random variables here. So if I try to do the direct transformation, I need to bring n minus 2 new random variables such that the transformation is 1 to 1, then I can use the Jacobian technique and so on and so forth. Or I can obviously use the moment generating function technique, but that will not be very easy because of all these square terms and then x bar here, again I have x bar here, lot of dependency there. So computation of the moment generating function will not be very simple. So how can I proceed? The way we will proceed is as follows. First, what we are going to do is that this xi has a IID normal 0 sigma square distribution. So from that, I can easily write what is the joint distribution function, joint probability density function of xi, which is nothing but the product of the marginals. And when you take the product of the marginal, it turns out to be this. And which can be written in this form also. It is basically nothing but this part is written in the vector notation. So this part is written in the vector notation. The reason is nothing but when we will proceed, we will see that writing in the vector notation is much easier in this particular case. Now what I am going to do is that I am going to transform the random variable x. I am going to transform the random variable x to y. Okay, the random variable x is transformed to y with the help of a matrix A. It is a n cross n matrix, so it is a linear transformation. Okay, so I am going to transform the random variable x to y, and I try to find out the distribution of y given the distribution of x. So what is the matrix A? Matrix A is an n cross n orthogonal matrix whose first row is 1 by n, 1 by n, so on and so forth, 1 by n. So all the entry of the first row are 1 by n. Okay, clear? So natural question is that does such a matrix A exist? And the answer to this one is yes. Why? Because I can start with this vector and I can extend it to a basis of r to the power n, right? And then on that collection of vector, if I run the Gram-Schmidt orthogonalization, I will get the matrix A. Okay, so this kind of a matrix exists. Which first row is 1 by n, 1 by n, so on and so forth, 1 by n, all the entries are 1 by n, and this A matrix is a n cross n orthogonal matrix. Clear? So if A is the orthogonal matrix, its inverse exists, and inverse is nothing but the transpose of A. So this, as inverse exists, this transformation is basically a one-to-one transformation. Okay, fine. So I can use the Jacobian formula in this case. Only thing I need to now find out what is the Jacobian of that inverse transformation. So inverse transformation in this case is nothing but x equals to A transpose y, because x equals to A inverse y, because A inverse equals to A transpose. That's why it is x equals to A transpose y. Now note that in this case. So when I find out the Jacobian, that turns out to be nothing but the determinant of the matrix A transpose, which is same as the determinant of A. Now, as A is orthogonal, that means determinant is either +1 or -1, but that does not change anything because finally I need to take the absolute value of the Jacobian. So absolute value of the Jacobian is 1. Okay. So let us now see that what is the distribution of y, what is the joint PDF of y. So the joint PDF of y using the Jacobian formula is nothing but f of x, that x needs to be replaced with the inverse transformation multiplied by the absolute value of the Jacobian, which is 1 in this case. So now just plug in A transpose y here in the state of x, take this A transpose outside common, then basically we will have A transpose here, which is going to give me I, because A and A transpose are A is orthogonal, that's why this is going to be I, and neta is nothing but A mu. Neta is nothing but A mu. So I just take this A transpose from here, A transpose from here, I get okay. So that means that, okay, so I have that the joint PDF of y is given by this way. I'll make more simplification of joint PDF of y, but before that, let us little bit see what are the values of neta 1 to neta. So first one, neta 1, that I can find out very easily because mu is basically all the components are mu. The mu vector, all the components are mu, and A matrix, the first row is 1 by n, all the entries are 1 by n. So neta 1 is nothing but one this row vector, this vector multiplied by the mu matrix, mu vector, right? This vector multiplied by the mu vector, and that will going to give me root n times mu. Clear? So neta 1 is nothing but root n times mu. This is nothing but the first row of A multiplied by the mu vector. So which is root n times mu. Now you see that neta transpose neta, which is basically mu transpose A mu, and because A transpose mu is I, is basically same as mu transpose mu. So neta transpose neta and mu transpose mu has the same value. So that means that summation neta I square I equals to 1 to n is same as summation mu I square I equals to 1 to n. Because mu I has all the components are same, so that will going to give me n mu square. That means I equals to 2 to n mu neta I square is same as n mu square minus neta 1 square, and neta 1 square is nothing but n mu square. So that means the summation of a neta I square I runs from 2 to n is equals to 0, which shows that neta I equals to 0 for all I equals to 2 to n. So this neta matrix, neta vector, the first component is root n times mu, the rest of the components are 0. Okay. Now use this one to simplify this function little bit, and if you put this one here, that first component is root n times mu, the rest of the components are 0, you can easily write that this joint density function can be written in this form. The first component corresponding to y1 and neta 1, y1 and neta 1, and the rest of the components corresponding to y2 to yn, they are no neta present because neta value is here. So what we got? We got that the joint density function of y can be written as the product of the marginal density function of yi. That means yi's are independent. Okay, and the distribution of y1 is normal with mean root n times mu and variance sigma square, and distribution of y2 to yn are same, and that is same as mean 0 and variance sigma. Okay, so we got that y1 to yn are independent random variables. Y1 has normal with mean root n times mu and variance sigma square. Yi has normal distribution with mean 0 and variance sigma square for all I equals to 2 2. Okay, clear? Now you say that what is y1? Again, y1 is nothing but first row of mu a multiplied by x vector, and that again going to give me root n times x bar. Clear? So that means that root n times x bar, because y1 follows this, that means root n times x bar follows this distribution, and this implies that x bar follows the normal distribution with mu variance sigma square by n. Clear? So one of them we have already done, that we have shown that x bar follows a normal distribution with mu and variance sigma square by n. Now let us try to find out the distribution of a square. So before finding out the distribution of a square, again notice that y transpose y is same as x transpose. The reason is nothing but y equals to ax. Just plug in this here and you will get it. A is orthogonal, you will get 1. Now again in case of the neta, I can write that this implies that I equals to 2 to n summation of yi square is same as I equals to 1 to n xi square minus y1 square. Now y1 is basically root n times x bar. Plug in it here, I get this nx square, and this quantity is same as n minus 1 times x. Okay? So n minus 1 times x square and summation yi square I runs from 2 to n is basically same thing. What is the distribution of yi square? The distribution of yi is normal 0 sigma square. They are independent and they are IID. For I equals to 2 to n, yi are IID normal 0 sigma square. So that means yi by sigma will going to follow normal 0 1 for all I equals to 2 to. Okay, so yi by n follows IID normal 0 1 random variable. So now if they are normal IID normal 0 1 random variables, that means n minus 1 times sigma square square divided by square, which is summation I equals to 2 to n yi by sigma whole square This is basically standard normal random variable. So this summation will have a chi-square distribution. And how many random variables are there? The summation is from 2 to n. So there are n minus 1. So that's why that n minus 1 times a square divided by sigma square have a chi-square distribution with degrees of freedom n minus. Okay, so two things we have already shown, that x bar has a normal distribution and n minus 1 times square by sigma square has a chi-square distribution. Next thing we need to show that x bar and s square are independent. And this one is very easy to show, because see that x1, x bar, here we have shown that x bar is a function of y1 only, and s square is a function of y2. X bar is a function of y2 to yn only. So x bar is a function of y1, s square is a function of y2 to yn, and we know that x bar and y2 to yn, these two partitions are basically independent. That's why the function of x1 y1 only and the function of y2 to yn only will going to also be independent. That's why x bar and s square are independent. Okay, so this proof is quite interesting. It is not a direct proof, but I mean, what should I say? A very interesting proof, and a proof is not a direct, but that proof, in my opinion, this proof is very interesting and clever proof. Okay, with that I stop at complete chapter.